So hey guys, I'm Jason. Tsushiki. We're both developers at Mastery Connect. I was the co-instructor at DevPoint Labs for almost a year. Went to the course before that. Been with Mastery for about 6 or 7 months now. That's me.
Where are you from, Jason?
Oh, I'm from Seattle. Yoshiki, where are you from?
Oh, I'm from Denver, Colorado. Just moved here a couple months ago. I've been coding for a little less than 2 years now. So, I've been at Mastery Connect for 9 months, I think.
Yeah. Cool. So, we wanted to talk about our botnet that we built at Mastery Connect. Basically, the background on this was that our site had some performance issues that we were trying to debug, and we wanted to see if we could figure out a way to simulate a lot of users on our site simultaneously.
Really, really heavy load. A lot of people hitting the site all at once.
Yeah, and so we decided, we found a few tools. We found Locust.io was an example. We found there's one to go that we could possibly use as well. And so what we ended up doing was deciding to build our own. So in one kind of fever pitch night, we built it out and ended up using it successfully in that testing. So for load testing, you need to open a lot of simultaneous connections, right? We were having a lot of people kind of click on stuff at once was sort of the original thing. We hadn't actually integrated load testing into our development at all. So we decided to kind of simulate that. So we wanted to simulate a lot of machines. We wanted to be able to have them all hitting something all at once. So we kind of settled on a botnet for what we wanted to build and how we wanted to attack our site.
And one of the key elements is that each visit had to happen simultaneously to get the maximum load per visit out of it. So one of the big questions was, how do we coordinate this network of machines so that they're all hitting the same thing as close as possible?
Cool. So this talk, we're going to talk a little bit about distributed programming. We're going to talk about the TCP socket and TCP server class that are built into Ruby. We're also going to go over threads and queues and how we use those and a little bit of kind of gotchas that we ran into. And then we have a master-slave architecture that we've kind of built out, so we'll explain what that is and why we decided to go with that. And then for our user simulation, we went with a gem called Mechanize that allows you, similar to Selenium if anyone has used that. We went with Mechanize because it was headless primarily, so we could run it without any kind of browser or having to spin up a JavaScript rendering engine. But you can swap it out with really anything you want. So anyway, let's get started and talk about the overview on how this works.
So this is the basic architecture of the botnet. What you have here is a single server that's going to coordinate the actions of every single machine. And then within a single machine, you have one thread running called the supervisor. The supervisor is going to receive commands from the server, and then it's going to hand those over to additional threads that are called bots, which are going to actually execute those commands. So in the next slides, we'll go a little deeper into that.
So this is kind of a more in-depth view on kind of how we orchestrated this. So basically, the server will start up, and you pass in a bunch of command line arguments, such as how many threads you want it to run, or how many threads you should expect, where it's going to be, its host and its port, as well as what routine you want to run. So we'll show you that in action in a little bit. And then you create all your supervisors. So each supervisor has a command queue for every single one of its bots. And so that's kind of how we were using queues. We also have a response queue in there. So essentially, as the supervisor receives commands from the server, it passes them to each of the command queues for each of the bots that it controls. The bots then execute it, so they go do their HTTP request and response, and then they pass whatever details you want to go back to the response queue. So an example might be a page status node, or any, say you created a post during your like we're going to show you a blog example. So if you created a post, you might want to save that ID so you can maybe create a comment associated with that post later. So they have a way to keep state that at the moment is kind of sketchy. We'll show you why we did it and how it works. But you can theoretically go through a whole workflow on a site and save information as you go, and those will be saved with bots. Anything else you'd add into on that issue?
We're going to go over each individual piece of this and then review afterwards. So if none of this makes sense, Don't worry, that's why we're here.
We'll explain it. We put all the code up on GitHub. We're actually planning on open sourcing this under our company's account. So we're going to we have sort of a work in progress version, but we're going to make it a lot easier to deploy, and we're hoping that people will actually contribute to this and work on it and maybe integrate it into their workflows. So here's kind of the main intuitions that we want you to get. Is you have one supervisor that is going to orchestrate all the commands. You have many different machines with one supervisor per machine, and then each thread has each machine has many threads with one bot per thread. That way you can have a bunch of things running simultaneously and simulating load the way that you want. So the first part of this is TCP.
So TCP stands for the Transmission Control Protocol. Basically, most of the communication you do over the internet is either TCP or its close relative UDP. TCP is really nice because it is reliable, ordered, and error checked. So reliable means that if you transmit a package, you can be fairly certain that's going to get there. Ordered means that things will come in the order that you sent them. Error checked, so TCP packets, I think, are sent in 8-byte packages, and each of those packages have a checksum associated with them. So without getting into the details of that, it adds a little bit of overhead, but when the client receives something, they can actually check one of the values in the packets and verify the integrity of that packet. So you know for the most part that things are always going to be coming in the right order, and they're going to be completely valid packages. And it'll do the retries and all that stuff for you. HTTP, for example, is commonly implemented on top of TCP to do communications. So HTTP is a protocol on top of TCP. Although it can technically be implemented on other ones as well. Another nice thing is Ruby has in the standard library a TCP server and TCP socket implementation that you can use yourself. Basically everything that we've done here is all stuff using the standard library. The only gem external dependency that we have is mechanized for the actual interaction part. So this is from the Ruby documentation. On the left you have a client. On the right, you have a server. You can imagine running each of these on different machines. So you open up a server on the right, and that's the socket that you're going to be running it on, so 2000. And the server has an accept method that you're on. What's going to happen is any time someone makes some kind of connection to that, so you can actually just put this in your browser and hit whatever this IP address is with the port 2000, and it'll actually accept the connection. And it'll just return the string hello, as well as the current time, and then it closes the connection. Over there, on the client, all you need to do as a client is open up a socket, and then call this gets method. Gets is going to block on any new incoming TCP message. So once that message comes in full, it'll run that, put in the variable line, and then print it. And then afterwards, so sockets are like files essentially. In Linux and Mac OS, they're actually virtually files, so you can open them and close them as you please.
I want you to talk about at the very end kind of a gotcha that ended up causing for us as we were kind of starting building this. All right. So I'm sure most of you are familiar with threads. Ruby has threads built in, but they're not truly parallel threads. They're kind of, I forget the exact term on that.
Ruby doesn't have green threads. Yeah, they're green threads. There's not true concurrency. So if you're dealing with like C or C++ or Java, for example, threads, if you make multiple threads, they're all going to run at the same time in terms of like computation and that kind of stuff. Ruby doesn't do that, but in our particular case, and in many cases actually, you can benefit from having multiple threads in Ruby because when you're making an I/O call to the operating system, the thread will be paused until the operating system receives whatever I/O you're waiting on. So you can run a crap ton of threads that are all opening their own HTTP requests or whatever, and instead of locking on each HTTP request, you're going to halt all those threads, and then they're going to be woken up once the request is available.
Exactly. So one of the things that we're looking to do in the future is maybe implement this into Ruby instead, which does have native threads. But for now, this has kind of solved our problem. So here's an example of a thread. So we would say 10 times map do and build out a thread for each one. That's just going to sleep for a random amount of time. And then puts hello from X, which would be the number of that thread, right? So you can, I mean, this is probably the simplest way that you could implement threads. One of the things that we use threads for, and we'll probably show this in our code later, is we have a response, listen for responses thread that's just constantly listening and looping through to check to see if it's gotten any responses back from its bots. And then we have each bot running a thread that's basically waiting for messages on their queue so that they can then go run whatever command they've been given. So queues are another integral part to our botnet. They're similar to arrays in that you can pop and push. They're also thread safe so that you can have any reads and writes simultaneously, but it won't get messed up.
Specifically, what happened in any order is guaranteed to happen in the same order. Like if you write a bunch of times, each time you write, you know that the next read is going to be whatever you wrote last. If you did that with a traditional Ruby array and you had like you had some pointer into the array like I, and you incremented it and incremented it, and you had multiple threads doing that, there isn't a guarantee that you would be able to, unless you implemented like a queue, there isn't a guarantee that things would happen in the order that you specified. With the thread queue class, this is actually part, when you do require thread, queue becomes part of that as well. When you use a queue, you know that things are going to happen in the order that you specified.
Another advantage for us is that when you have someone popping on a queue or kind of listening on a queue, it's going to halt execution of that thread until it gets a message back on that queue.
It kind of acts like a socket in that sense.
And so it will block, and then what you can do is have a bot sleep while it's reading the command. So that ended up being really useful, and you don't have to worry about your bot just constantly running and running and running. It'll only run once it's gotten a command from the server. Otherwise, the thread repeats.
And this isn't just a Ruby thing. In a lot of languages and a lot of like multi-threaded programming contexts, you're going to use queues.
So here's an example of a queue. Essentially, we're requiring thread, as you mentioned, this is part of the thread. We're going to create a new queue. So I didn't do this example. You want to walk through this?
Yeah, it's really similar to the server client thing that we had set up previously with sockets. In this case, instead of server, you call it a producer, and then instead of client, you call it a consumer. That's just traditional computer science terminology. Producer's running within a single thread, and it needs a random amount of time just to simulate like some kind of like intense computational task, and then it just pushes it on the queue. So one nice thing about this is that the producer can push on the queue continuously as much as it wants to. The consumer pops values off the queue as they become available and then does this computation. If this were some kind of, if this were like an actual real world example, and like the producer was handling some kind of expensive resource or doing something like really intense, and then the client was doing the same, the nice thing about this is that you can split those workloads separately. So as the client is able to do things, it can read stuff off the queue. That's a good example. You see this in compilers sometimes, where like you might tokenize a program and then just parse it. It's a nice architecture in general. One other thing is, in order for Ruby not to exit, so if you run this, this is all a single file. If you run this, you have to have the join at the end. So join is a method on thread, and it'll make the current main thread, because everything in Ruby runs in the main thread first. Wait for this child thread to finish, to exit, before it exits the whole program.
Awesome. So that
out of mind.
Yeah, so we can revisit this. So each of these response queues are queues essentially. We kind of talked about how the sockets work for the TCP server and client. Do you guys have any questions about this architecture in general? Or anything about threads or queues or TCP that we can answer? Theoretically, there's no limit, but not really. So the question was, what is Ruby's limit on threads? As far as I know, there isn't a limit, but you will eventually just kind of slow down your machine. Like we've gone up to like 100 is kind of the max that we've gotten to.
And there's also, so in our particular case, and in any kind of distributed computing, you have to be aware of the limitations of your hardware. Like most Linux machines, like say EC2 instances can't open like 1,000 connections on a single machine because it just can't handle that. What we found was like for typical hardware, like our laptops, we don't open up maybe like 50 or so sockets, I think it was, before like it just wasn't really getting much performance out of it. So more threads doesn't equal more performance.
So one thing on that, normally your threads have direct correlation with the size of your CPU. I don't know that there's a hard cap at all, like you see in language where you're at and you're on memory. But like I said, with MRI, MRI only runs on a single core, so you have a quad core machine and you're only using one program, right? So using JRuby, you can use all four cores.
Right. That's kind of why Ruby, at least the MRI implementation, is really the best solution for this. And so JRuby would be a lot better, and that's kind of what we're moving towards. We've also kind of experimented with Go, which has a lot of built-in concurrency that's really easy to work with. Yeah,
concurrency in Ruby is not a pretty picture, actually. We're weirdos for doing it in Ruby.
but we thought, what the hell, Ruby would be fun. And it worked out pretty good. So yeah. So we're using this to test our site. So we have Mechanized kind of a user agent gem, right? It's often used for web scraping. So each of our bots is using Mechanized to hit endpoints, right? So we might hit a controller action that's been particularly fussy. That way, what we've done is we've been able to say, let's hit it with 500 concurrent users, and we have new relics set up. I'll actually show you that in a second, and it'll show us kind of what our our expensive queries were, how long it took in the Ruby side, how long it took in the SQL side. And then we'll maybe we'll like work on improving and optimizing, hit it with the same amount and be able to see that difference. So a lot of it's for benchmarking as well as just generally trying to find weak points in our site and patch them.
Yeah. It's a little bit different from benchmarking, by the way.
Yeah.
Because you can do benchmarking locally, for example, and like, there's like a gem, I forget, like Typhus, that you can spin up, and like it will give you an idea for like some rough performance in your application. This is more like in your staging or even production environment, where you want to test how your database is handling load. You want to test how your load balancer is handling load. You need a lot of simulated users to do that, and this is what that accomplishes.
So yeah, we were having problems with our load balancer, for example, and then we were able to diagnose that and identify that with this tool, which was something that we wouldn't have been able to find out before. So we had our DevOps people like standing by watching as we were running this, and we ended up fixing that quickly and had no more issues after that with the load balancer. So I personally had a really hard time working on this because a lot of times my threads would die and I would be like, I have no idea what's going on. So things are going to fail, and so what we have is we have a few ways for the client to report back to the server that a bot has died, so the server can kind of adjust its expectations. For example, we have this idea of where we want to be able to hit, like, say, with 100 at once, and we wouldn't want any of the fast bots to then move on to the next action because we're trying to simulate concurrent users. So on the server, we have like a threshold that we set, so 90% of bots have to report back and say, hey, it worked, before we actually move on to the next step. So if you have bots that die, inevitably you do.
It's actually like the trickiest part.
Yeah.
Because if you think about like, how do you have like synchronization across any given number of machines? How do you make them all coordinate with each other? That's where the master slave architecture comes in.
Yeah, so the
Why we have the
supervisor
threshold.
is basically watching all the spots. We have sort of an is alive method where it'll just check all the threads and make sure that they're still alive every so often. If a certain status code comes back, like say a bot gets 500, that's not gonna. We're not trying to like rescue them and put them back on something else. We just say, okay, they got a 500, they're dead. Report that back to the server, and so then the server knows, okay, I lost 4 bots here, I lost 5 bots here, and it increments its bot count accordingly and updates the threshold accordingly. So you might start with 100 and you need 90 to report back, but eventually you might hit 50 and just need 45 to report back.
Yeah, and this makes you think about like how much you have to implement error detection and like failure handling on your own. If you're in a single-threaded context, if something fails, you're going to get an exception. It's going to boil up, and then somewhere you might have a big end rescue that you're able to catch up with, right? But when you're dealing with even threads on the same machine, things aren't going to happen in like that linear fashion. If you're talking about different threads on different machines, then you have to actually implement your own protocol to report like the current state of all your machines and how the system's going to react to that. So that's one of the big challenges of distributed programming.
So yeah, at the beginning we just had a lot of logging in every single thread, like what's this, you know, just anything that we could to kind of detect this. We would have it. You could kind of test originally with just like running one single thread per supervisor, and that made it a little bit easier to catch things. Like we actually were using pry in our threads, which was kind of interesting. But that once you're running at scale with tons of threads, you can't really do that anymore. And so you need to make sure that you handle failure gracefully, because a lot of times you're not going to know what failed. You'll just know that it did, and you have to move on. Otherwise, any number of things can totally mess up your whole project. So let's talk a little bit about the server as well. Essentially, the way that we have this set up is we have some routines files. The routines are for steps that we want it to take. So, for example, go to the home page, log in as a teacher, create a classroom, whatever. And so the server keeps track of steps you are on that routine. So we read in that file and break it up by line and kind of just create an array of the steps that we want to run. And server will transmit that command to all supervisors, keep track of how many return, and moves on once a certain percentage of the clients has finished. We also have added a little bit of logging to this so that it will send out to a file and so again, if bots die, the title, know to keep moving on.
We keep track of response times too.
Keeps track of response times. We're actually using this with New Relic, so a lot of our main data we capture on that side. But the goal is to just implement a ton of extra logging on the server. Yeah, another cool thing is that we've actually got this running up on AWS EC2 instances, so that we can basically do a code deploy up to AWS, and it will bring up our server, vision all of its clients, whatever we want, and then spin a second. Yeah. So essentially, the server will transmit a command. So we have basically at the moment we have visit and stop. And so visit will send whatever method we want. So we have our command set up as methods. So for example, we'll go to home page. You create a mechanized agent, we call it, and that would just do get home page or get a certain URL. And so it's basically we'll actually show you that it's sending to the bot a command to run, and the bot will run it. Yeah, that's about it on the server. Yeah, so that's kind of an example of BotNet's method. So server starts, waits for clients to connect, all clients finish connecting, broadcasts the command, supervisors distribute those to their command queues of their bots, the bots receive the command, and execute the command, and then write their response back to the queue. The supervisor then returns that to the server. And once the issue response is greater than a certain percentage, it moves on to the next step. So we've already kind of covered some of the failure scenarios. If a thread dies or a machine dies, we lose a connection. One of the problems that we ran into actually is we originally had all the client machines as just threads essentially. So we didn't have a supervisor opening the socket and relaying information back and forth. And so when we were talking about the file problem, we ran into this open file limit. Like, what's going on? We had each bot opening a socket to talk to them. So that was really kind of naive of us. And so we got a lot of errors that way, and then just sort of implemented the supervisor bot system instead. So in Unix, sockets are considered open files. And so we would run into file limits because we were just opening and putting it to sockets.
The system has this environment variable called like the open file limit, and if you try to open more files than that, you're going to run into issues. Like by default, I think it's like 1,500 or something like that. But a lot of those are already used by the system. So like maybe like 1,000 of those are already used. And then you try to spin up 500 threads on your machine to visit stuff. Say for example, double actually, because each is opening an HTTP socket to do the load balance testing, and they're additionally opening a HTTP socket to talk to the server. So that would like, because each bot is opening one socket for the HTTP connection that it makes to the website, mechanize for the load testing, and it also has a TCP socket open with the server to receive commands and respond. So if you have like 50 bots, you're going to open up 500 sockets. If you have 100 bots, you're going to open up 200 sockets. 50, 100, 51.
Doesn't make a ton of sense.
So you're in this error on the server.
Yeah.
Not necessarily.
Well, both cases.
You are because you're spinning up what? Different connections, 200 connections.
200, something like that, yeah.
I don't remember. Yeah, we moved on from that pretty quickly.
It could have been the server because the max we ran was like 200, I think. In the case of the server, it'd be just exactly 200. So
Yeah.
client it doubles. Yeah.
Cool.
So yep, you want to be smart with your resources.
I had something that I forgot. Maybe it'll come back to me. Another problem that we ran into. Okay. So we're going to actually run this thing and show you kind of how it works. And we've got basically a botnet target that I've set up on Heroku. You can hit any URL that you want as long as you know the endpoints or the URLs that you want to hit.
As long as you have permission to.
Yeah. Oh, that's what I was going to say. So what was pretty funny actually when we were testing this is we wanted to see if we could run a server in the cloud and then run our clients from our local machines.
Oh yeah.
And so
I set up a DigitalOcean droplet, and we tried like 200 connections or whatever. If you don't know DigitalOcean, they're basically like Heroku. They're like a cloud server provider. The issue was we were opening like ton of connections. We had like all of our laptops like participating in the botnet. DigitalOcean actually shut it down because they have all these algorithms to detect suspicious activity. And if you're opening a lot of connections like that, you're probably not doing anything good. You're probably running a botnet like we are. We got an email saying, oh, we had to cancel your thing because it was bringing down the system and you're probably doing something illegal or your account's been compromised and someone's running nefarious software there.
So what would be a better load balancing than this botnet, or just posting a forum on 4chan as some people decide?
Yeah.
well, if you could get 4chan to all agree to do it, then maybe. But that's unlikely.
4chan already has a very sophisticated botnet of their own.
Yes, the low orbit ion cannon.
Low orbit ion.
So if you ever hear DDoS attacks in the media, that ends up being what it is. It's actually pretty easy to find and download on your own. I do not recommend it, but it's fun. So I mean, this is a distributed denial of service tool. So you can totally bring down sites if you have enough manpower. Yeah.
So, like, why did you build this instead of just using one of those denial of service attacks? Would that not do the same thing?
So yeah, kind of. DDoSing, all you need to do is hit a single page like 1,000,000 times. That's all you need to do. You don't even need to hit the page. You just need to like open a connection to that port and download something. So all the DDoS tools do is they just like hit like URL and that's it. Our thing, the whole like idea of the tool comes into this idea that like, oh, you have to log in, you have to perform these actions, you have to do like basically stuff similar to like acceptance testing.
So you normally use it on the website.
Yeah, as like a real actual user.
Yeah. So we need a lot more precision. We needed to be able to like say we're creating like, so we do educational software. So one thing that we're struggling with was we create curriculum maps, and that ends up being like pretty expensive. And so we wanted to be able to create those programmatically so that we could then monitor all the Ruby code that got executed, all the active record queries that got ran, and see if we could find any ones that we could strip out or optimize.
If you're just doing like straight DDoSing, then like you can test your load balancer, I guess, but actually testing your application and your database, you're not going to get much out of it.
Yeah. So with Mechanize or Capybara or Selenium, all which can be ran headless or run headlessly on a server, you can fill out forms. You could just send a post request with params if you already knew what that controller in Rails' case was expecting. And so it's just, yeah, a lot more sophisticated and precise. So we're not actually gonna log in, create a post, and create a comment on the post. I actually set this up so if you want to download this and play with Mechanize, you can. So it'll have those methods ready to be implemented. But we're gonna try this out with about 20 users. So first things I wanted to show you kind of how the Mechanize portion of this works. So what we have in our BotNet file is the server here, the supervisor here, which, oh, actually we didn't do that, and then the bots here. So the bot is kind of the simplest one to kind of look at. So essentially they initialize with like a secure ID, like a random ID, so that you can keep track of them and work with them. And then they get the response queue passed to them via the supervisor. And they spin up a mechanized agent and a hash for state. So the reason for that state hash is that you can then use that to save any IDs or things that you need for other parts in the action. So essentially you run, you use the run method inside of a thread. And we put that as an adder accessor so that the supervisor can just query all its bots threads to get status on them. And then it just waits for commands, starts.
So that main loop should be familiar from the queue example.
Yeah, it's very
The main
similar.
thing that's happening is just the queue.pop is just blocking on new commands being received on the queue.
Right, so it'll just wait right here if it doesn't get anything, and then it'll move on to the next thing. So we have a start time and an end time so that we can just pass like this action took 3 seconds or whatever. And then we basically just send whatever command we receive to itself. So self.send is just a way to call a method without maybe explicitly knowing what that method is going to be. So in this case, we pass it the agent and the state so that it has its mechanized agent to work with and its state to send things. And the way that that's working is with these routines. So the routine is just a series of methods that gets read in by the server and broken up into steps. And these methods correspond to a commands module. So this is kind of our commands module. And so we have go to homepage, right? And the very basic thing you can do with Mechanize is just go agent.get and pass it a URL. And that would just be hitting a site. Additionally, so we just have one set up right now to go to the home page, go to the about page, go to posts, and go to a specific post. And in each of these, they're saving to the state whatever page code they got back, so a 200 or 404 or whatever. And we kind of created a little test app that we're going to run this against. So it's just a very basic blog. I use Dusham Ipsum because we're just assuming that this is some guy that we really don't like and we want to bring his site down. So it's kind of cool. I didn't even know that existed. There's all these Ipsum things. But yeah, I mean, it's just like your very simple scaffolded out Rails app with an index and posts. Ooh, someone deleted that. So I need to maybe go and change this to 2. Nice touch with the comics. Oh, Dan. He must have messed it up when he was up in the, someone did. Anyway, so we have this hooked up to New Relic as well, so you can actually see stuff in real time. It takes a little bit to load, but this is just our setup for monitoring things. So let's go ahead and try this out. So hopefully you can see this. We have 2 kind of upstart scripts for this. So if we check those out, there's start client and start server. And so basically what we do is we set up some command line arguments so that you can pass in a host, a port, any threads that you want to run, and then a timeout, which we're actually not using at the moment, so we could get rid of that. And then we just create a new supervisor with those options, and off it goes, right? So we also have that for the server, which is a little bit more sophisticated as we need how many threads it expects, what percentage we want to return before it goes on to the next step, as well as the routine that you want it to run. And then we also have this EC2 option if we wanted to run it on EC2. That is also stripped out of this version as we had to remove some of our stuff from work. But we're going to try and bring that back in to the open source version as soon as we can. And then it reads in the file of the routine and maps it into just like an array and then starts the server. So without further ado, here's my start server. So I'm going to go ahead and start that up. And you can see that it's running on localhost and waiting for 20 bots to connect. And I'm going to start each of these clients. So you'll notice that it connected a client. The client did like a basic handshake procedure with it and said, here's who I am, here's my ID, I have 10 bots. Cool, so we now have 1 client and 10 bots. And as soon as we start this next client, it's probably going to run pretty fast because there's not a ton of meat to this application. So, boom, they're receiving the step. And these are them reporting back all of their processes and basically who they are, what command they receive, and the status they got back. And so you'll see that the client actually reports it. It just kind of puts it out, and then it gets passed along to the server. So the server's getting like a response. Hey, a bot with this ID executed this command, got a status of 200, and it took it 0.3 seconds. Cool. So
Keep in mind, this is all happening locally, but it would also work on separate machines completely fine.
yeah, so we didn't set that up, but if I set it up on my IP with my port and gave that to Yoshiki,
laptop, then
boom,
like, yeah.
we could all hook up. We could have all of us hook up to it if we wanted to. So that
board.
Yeah, it's pretty cool. Yeah, we could be the board. And so once it's done, it says ending Operation Lightning Bloodhound, which was just a dumb code name that we made up, but we kind of like it. We'll probably incorporate that into the official name.
It's not a dumb name. I came up with it.
I think it's kind of dumbish. But, and then as soon as they receive the command stop, the clients exit out, server exits, and it's all done. So yeah, that's a basic run of it. You could run it on your local host as well. That's actually ends up being kind of interesting as well because you can see the server log going crazy as it's working. But hopefully,
show up in New Relic.
This might take a second, but you can kind of see there's a little peak here that's starting up, and so that's probably our botnet hitting the website. Douchebagblog.com. It's actually botnet-target.herokuapp.com. I was surprised I could get a name that didn't make any sense, or that made sense instead of the nonsensical stuff Heroku usually gives you. But yeah, so we would use this. It will typically have like a list of recent transactions that you can look at in New Relic. So we'd be able to see like, okay, we went to our post controller and the active record portion took X amount of time. The SQL portion took X amount of time. It'll actually break out all the queries that you have. And that ends up being incredibly useful for load testing.
Reload. There it goes.
Yeah, so maybe it was pretty fun though. We had a great image of, yeah, so you'll see right here's the post controller show. It took 24 milliseconds to respond. Most of our transactions are middleware, and we're just running on one web instance on Heroku. Heroku actually has a free version of New Relic built in, which is kind of cool. It takes like probably 5 minutes to set up. And this has been really quite an awesome tool for us at work, and a good way to kind of show it. So you'll see, yeah, here's that traffic coming in.
So you see these like green bars. This is technically an area chart, but most of it's in the green. And the reason is that's the request queuing. Since these aren't really beefy instances on Heroku, we're pretty much overwhelming it. So all the requests are going onto a queue to be like, so that they're going to wait to be processed by the server because the server can't handle that many requests at once. So our application isn't even really doing much, actually. It's mostly in this request queue right here. Oh, there it is.
So they all queued up. We should have bought some more instances beforehand. But anyway, that's the botnet. We put a link to all this stuff on Git. Well, it should be at the end of our presentation and the Meetup group. But yeah, so that was with 20 users. The most we've done is with 200, I think, maybe, or I can't remember. But we actually were trying our staging server one time, and which was kind of a smaller. I think it's like a medium Amazon instance, and we pretty much brought the whole thing down, which was awesome because you really don't expect your staging server to ever handle a ton of traffic. So it is potent. Use it wisely, and if you want to fork this and use it for your own purposes or contribute, we're going to keep working on this. We're trying to get it so that you can pass, like have an interactive command line version of this on your server or integrate it into your continuous integration. We've kind of been playing around with getting it to work with Jenkins CI, for example. Yeah, it's pretty bare bones, but we had a lot of fun working on it, and we hope you guys enjoy the talk. So yeah, thanks guys. Cool. So yeah, if you have any questions, now's the time. We can show more of the code if you want to like go into the server and the client a little bit more.
Got a pretty good amount of questions throughout.
Yeah. Cool. All right.
Shy crowd.
Well, that's it for us then. Thanks, guys.
Thanks, Hector.
Cool. So we have a little bit of time if anybody wants to live talk.